So today we are going to talk about again the robot robot path planning problem, but this time we are going to look for shortest path. Okay, I mean we cannot say the shortest path because there may be more than one shortest path existing. So our goal is to find a shortest path between a goal position and between a start position and a goal position. Okay, so let's try to remember the last week's solution. What we were doing was we were first finding the free space, free configuration space. Where can the robot go? Where can we put this reference point of the robot? Which are the positions? So we are again going to talk about translational robot, no rotation. So we are going to translate a robot. So the allowed places, the legal places the robot can move is called the free space of the configuration space. So the first thing we did was compute the free space, and then we use a trapezoidal map to divide this free space into trapezoids, and we then build ourselves a roadmap in which we put nodes in the centers of these trapezoids, and we also put nodes at the middle of the edges that connect two trapezoids. So we construct ourselves. So here's a simple example. So here's a simple example. We have a couple of obstacles. So what we do is just assume we are dealing with a point robot. I mean, a rectangular robot, the only distinction is that this C free space, which is here, is extended by the Minkowski sum. So that was what we were doing if our robot was not a point robot. For simplicity, we can just assume we have a point robot. So therefore, the free space is equal to this box subtracted by these obstacles. So the trapezoidal map, what it does is we extend these vertical extensions. And until we don't, or for example, this node also has a downward vertical extension, but since it's inside the obstacle polygon, we just don't consider the vertical extensions that are inside polygons. So vertical extension of these vertex, this vertex, like this vertex. Again, downward extension is not considered. Okay, so these downward extensions, since they are not in the free space, these trapezoids are not part of our free space. We just delete them from our list. Again, this one and its upward extension is ignored, and it's like this. Okay, so these are our trapezoids, and we have nodes at the centers of these trapezoids. And we also have nodes in the middle of these edges between two trapezoids, and we connect them. We connect each trapezoid center to its to the nodes on its edges. Okay, so it's like this. We have two of them here, another one here. So this is our roadmap. Just first put all these. Okay, so this is our roadmap. And when we are given a start point and a goal point, we first, the algorithm first finds which trapezoids they are contained in. Okay, it's contained in this trapezoid, this is contained in this trapezoid. It first connects it, let me use a different color. So our path is like this. We first connect start to the center of that trapezoid, and then we connect also the goal position to the center of its trapezoid. And then what we have here is a node, and nodes are connected with edges. So this is a graph. So we can use breadth first search or any, you can even use shortest path algorithm on this. Breadth first search and shortest path are the same algorithm anyway. So what we have here is that we find a path to ourselves that is going to traverse the nodes of this graph, which connects the start node and goal node. Okay, and as you can see, such a path that follows this roadmap we constructed is not necessarily a short path. So we discussed this last time. So the fact that we are using the centers of these edges, for example, if you want to go here, if this node sees, okay, this is an important term. If this node here, actually, for example, it can see this one, okay, this node here, let me name node 1, node 3. Node 1 can see node 3 directly. So the shortest path, the shortest route between two nodes that can see each other is the direct line segment between them, right? So why go? Why extend the path to these other node if this one sees and one sees entry, and if you are going to follow this path, this is a shorter path. So following these nodes is going to give you a longer path. Now, today we are going to talk about how can we find the shortest path between these, and we are going to construct a different roadmap this time. It's not going to be trapezoidal map. First, we need to think about how the shortest path between this start and a goal position. If you are going to find the shortest path, how does that shortest path look like? Okay, which intermediate point is going to pass through. So, for example, if P start sees P goal, okay, it means that the line segment that connects these two is the shortest path if they see each other. But these obstacles, that would be a trivial problem. If I see from the start, if I can see the goal position, I don't need to consider any obstacles. I can just go there. Okay, but if there are obstacles, what will happen? How does this path look like? Okay, if there are obstacles. Yes. Any suggestions? Yeah.
Maybe we should first think there is no obstacle.
Yes.
So, the nearest point we can go.
Okay, very good. So this is the idea is really good. So I'm going to erase this trapezoidal map. So this was just for a reminder. Now let's think about this. We have a starting position and we have a goal position. So initially, think of this path as an elastic rubber band. Okay, so this when you put an obstacle here, what happens? Okay, what your friend suggests is that in order to go from P start to P goal, what we need to do is we need to somehow, for example, if this could be a path, okay, but is it a short path? Is it the shortest path? No, I can move this point towards the obstacle a little bit more, which is going to give me, for example, if you just consider this, okay, this is going to be a shorter distance considering these two, okay? So we can actually continue doing this until we hit an obstacle vertex or obstacle edge. So, and if you actually consider this as an elastic rubber band, which tries to shorten itself as much as possible, it's going to stop when it hits obstacle vertices or obstacle edges. So, and we have the following observation, and this lemma, there's a proof of this in the book. It's just a textual proof. It describes by examples like this, by counterexamples like this. If the path, for example, the dilemma is this. If we are given a set of obstacles with total n edges, and the path from the start to goal is composed of, it's a polygonal path. First of all, it says that it's composed of line segments. Okay, this path is composed of line segments. It's not curved. The lemma says it cannot be curved. It's a polygonal path, and its inner vertices of these polygonal path. The inner vertices of a path is so a polygonal path is going to look like this. Okay, so you're visiting some other points. These intermediate points along the path are called inner vertices. So these three are the inner vertices of this path. So what this lemma says is that this inner vertices of this path are the vertices of your polygon obstacles. And first of all, it proves the fact that it's a polygonal path. If it was something curved, okay, if there was a curve, for example, if it was something like this, this says that since this curve, since it's going to be a valid path, it has to be in the free space, okay? If this curve is in the free space, there must be a point on it, which is also on the free space. And we can enlarge this neighborhood of this curve because some part of the curve should also be in the free space. So we can continue enlarging a circle around this P until we hit an obstacle. So, and what we find is that we can actually directly connect these two other points on the circle directly with a line, which is going to shorten the path. Okay, so if you have a curved path, you can show that it's possible to shorten that path. So a curved path cannot be a shortest path. The first part of the proof shows that it's always going to be composed of with line segments like this. And also the other part of the proof, I mean, consider a vertex in this polygonal path. If it's not a polygon vertex, obstacle vertex, again you can make it closer to the obstacle vertex, and it's going to shorten the path. So this proof by contradiction shows that our path is composed of a path in which the inner vertices are polygon obstacles. What about the edges on this path? Sometimes there are line segments in the free space. Sometimes we may be grazing a polygon edge. I mean, it may be, for example, if it was something like this. Yeah, let me have a square or a rectangle. For example, let's assume I have something like this. Okay. Now, this line is parallel to this edge. Okay. In that case, the shortest path can look like this. This is one inner vertex. So vertex 2 and vertex 3 are the inner vertices. And vertex 1 and vertex 4 are the goal vertices. So sometimes this path and edge on this path may coincide with the edge of the obstacle. So we maybe, again, think of this as an elastic rubber band. Some edges may be the polygon edges themselves. Okay, now the question is, now we know how the path looks like. Okay, it's going to be, our shortest path is going to be the polygon vertices. Okay, so now this fact, this observation leads us to construct a different roadmap. So since we are going to this polygonal path, we have these inner vertices as polygon obstacles. So our roadmap should be composed of nodes which are polygon vertices. Okay, so we are going to construct a graph, a roadmap, in which the nodes in this roadmap are going to be the polygon obstacle vertices. Okay, so put all the obstacle vertices on this roadmap. Now the question is, where are we going to draw edges on this roadmap? Okay, so for example, from a vertex, which other vertex can you go? Okay. And this brings us to the notion of visible vertices and visibility graph. So when we are at a vertex, all the legal moves we can make are going to be to the vertices in which the line segment between these two vertices does not intersect with any other polygon, obstacle polygon. Okay, so in other words, whether given two vertices in this graph, in this roadmap, given two vertices in this roadmap, can I draw a line between these two vertices safely without intersecting any other polygon? So do these two vertices see each other? Okay, therefore, the visibility graph is a graph in which it has all the vertices and it has edges between any two vertices which can see each other. Which, if one vertex is visible to the other vertex, we denote this by an edge in this graph. And if we have this visibility graph, our problem then reduces to finding the running the Dijkstra's algorithm, shortest path algorithm, on this visibility graph. The weights of the edges are going to be the Euclidean distances between the two vertices. And by using the Euclidean distance and by finding the shortest path on this visibility graph, you are going to find the shortest path between your start and your goal. Okay, so now the overall algorithm is clear. But the thing we need to still solve is that how are we going to compute whether two vertices are visible, a vertex is visible from another vertex or not. And a brute force solution is there's an n-cube solution. So take every pair of vertices in this graph and just check this line segment with all obstacle edges, whether it intersects or not. If it doesn't intersect any obstacle edge, it means that these vertices can see each other. So there are, if I have n obstacle vertices, I have n obstacle edges, okay? A number of vertices of these polygons. Since these are polygons, the number of vertices and the number of edges are on the same, they are both On. For example, if this one has n vertices, it's an n-gon. So it has n edges as well. So what we are going to have is that for any pair of vertices, there are n square such pairs. I'm going to check them against n edges. Okay, so in total, the total running time is going to be n cube. So you can have an n cube algorithm which can give you the visibility graph of a pair of a set of vertices. Now, in the rest of this class, I'm going to talk about how we can reduce this n cube to n square log n. Okay, and then maybe in the second hour, since in the first hour we are going to be finishing with this algorithm, and that's the whole chapter. And in the second hour we are going to discuss other, maybe if some restrictions, if our polygons were our obstacle polygons, if all of them were convex, okay? If the algorithm I'm going to describe first is a general algorithm which can deal with any polygons, even polygons with holes in them, concave polygons, non-convex polygons, but this n square log n algorithm we are going to see maybe in the next hour. We are going to discuss together. I don't also know the solution to it yet. If all the polygon obstacles, all obstacle polygons were convex, could we have a faster algorithm by making use of this fact? Let's first discuss the n square log n algorithm. It's a plane sweep algorithm, but this time we are going to do a rotational plane sweep. So it proceeds like this. If our goal is, if somebody asks you, if somebody gives you a pair of vertices, okay, V1 and V2, okay, and asks you whether these two vertices see each other or not, the best you can do is to check with all the, you cannot avoid n square here. If you're just given a, you cannot avoid checking against ON edges. If you're given a specific pair of vertices, if somebody gives you these two vertices and asks you whether V1 sees V2, you need to do this check. You need to check against all the polygon edges. But now, again, we are going to make use of the coherency fact. If instead of dealing with all these pair of vertices separately, let's ask this question. Just pick a specific vertex. Which other vertices this vertex sees? Okay? Now, it's, in other words, instead of just asking this, okay, I mean, these may be something like this. I can have, let's have these as our polygons. Okay. And this may be part of another polygon. Now, this is V1. And instead of asking whether V1 sees V2, just imagine we want to find, since in order to compute this visibility graph, we need to find the visibilities between every pair of vertices, okay? So we cannot avoid n-square complexity because your roadmap at the end can have n-square edges between them. I mean, you have n vertices. If all the vertices can see each other, okay, if you have, or your obstacles are so dispersed and your polygons are very small, everybody can see everybody. Okay, in such a case, you are going to have in your roadmap n-square edges anyway. So your roadmap's complexity at most can be n-square. So therefore, we are going to, I mean, this is like a lower bound, but let's see if we want to find out not only this, we want to check not only this line segment, whether it intersects other polygon edges, but we want to do is for V1, for all the vertices from V1 to every other vertex. Okay, so if we do it, if we ask this question for V1, whether so these are the line segments that I'm going to check for V1. Okay, these are all the line segments. If I want to find out whether V1 sees these vertices, these are the line segments that I'm going to draw, and I'm going to check all these line segments against all the polygon vertices to see if I see every one of these other vertices. Now, for example, take a look at these two vertices. Let's name them. Yeah, one of them was V2 and this is V3. Okay, and also take a look at this one. Let's name it V4. Okay, I see V4. Okay, V4 there's not intersects with nothing. But when I come to V2, I realize that these two edges intersect with V2. But the same edges intersect, actually not the same edges, but this long edge here also intersects with this V1, V3 line segment. So can I make use of the fact that V2 and V3 are close here? I mean, and the same line segment occludes, obstructs our view. The same polygon edge obstructs both V2 and V3. So can I make use of this fact somehow? So this is some kind of a coherency. So instead of having ON square computations for V1, can I reduce it to, for example, n log n computations? If I can reduce this to ON log n for V1, for all the other vertices I'm going to do this again, the total complexity is going to be n squared log n. Okay, so when you see n log n, you immediately see sorting, okay? So n log n is probably something we can have a solution related to sorting. So if somebody asks you this, find an ON log n solution for this problem, the first thing you're going to, so can I sort these points somehow? And if you look at these line segments, a natural sorting is, like in Graham's algorithm, is a rotational sorting, okay? If you consider the angle they make it with the positive x-axis. You look at each of these line segments and you look at the angle they make. So our event points, so we are doing now again a plane sweep. This time we are rotating in this pivot point V1, we are going to rotate a half line 360 degrees, and during this rotation we are going to jump from event point from vertex to vertex. So our vertices are going to be the event points. So we are going to process this line segment first, this one next, this one next. So this is going to be our rotational sweep in this algorithm. So what about our status structure? What are we going to maintain in this status structure? What's the natural thing? For example, look at this line here. What is its status? The polygon edges, the obstacle edges that are intersected by this line. Okay, so our natural the structure of this half line. For example, this one here, the first one with the positive x-axis intersects with these two edges. So when I put these the currently intersected polygon edges by this line, when I come to a new vertex, all I need to do is, my goal is, if I want to find out whether V1 is, whether this V5, for example, when I come to this V5, if I want to find out whether V5 is visible from V1, what is the constraint that makes this visible? The thing is that in the current study structure, there shouldn't be any line segment closer to this. If I compare, I just locate this V5 on this study structure. Where does it fall to? And it should, if it's not the nearest point on the status line, if there are other line segments which are closer to this, then it means that this line, this polygon edge, occludes V3 and V5, and I cannot see it. So a good, maybe we can also discuss this. But the book says these edges can actually be stored in a binary search tree in terms of their distance to V1. So if this half line intersects a number of polygon edges, we are going to, in the study structure, we are going to store them in a binary search tree in terms of how close. It's a binary search tree because we want to locate this V5 if we want to find out whether it's, maybe it can even be a priority queue or like a heap, because all we're interested in is the closest one, whether V3 is closer than the closest one or not. Okay, so I mean, we can just pick up the closest line in the study structure and check it against V3, and this check should be enough for that. But what about insertions? For example, when we come to V3, this new obstacle edge starts intersecting with the line that we are rotating. So we need to add this to this study structure. But priority queues are also, they allow log n insertions, right? So I think it can, I mean, it could have been done with a priority queue as well. So it's just a choice of implementation. You're either using a binary search tree or, but the heap, I mean, the visibility checks can be made faster in a heap. I mean, it's all one, just looking at the closest one. Just you are going to be looking at the root of this node to determine whether that current node is visible or not. Because we were not interested in the close R. The question is, in the previous plane sweep algorithms, why didn't we use heap but binary search tree? Because the next event point could be located anywhere within this structure. I mean, it's not necessarily, we were not looking necessarily at the top structure. We were looking at neighborhood queries. We were locating the next event point and we were looking at its left neighbors and right neighbors. We weren't interested in the top event point or bottommost event point in this structure. But here, what determines prevents the visibility of V5 is going to be the closest edge to this V1. So if there's an edge which is closer than V5 to V1, then we are going to decide that V5 is not visible. But even there is no such edge, we are going to consider some extreme cases. I'm going to talk about some extreme cases in which in some cases V5 will be visible, and in some cases V5 will not be visible. Let me... Okay, if there is such an edge in between, it is certain that it's not visible. Okay, but if there is no such edge, there may be still cases. I'm going to draw this now, in which, okay, so let me, the general outline of the algorithm, is it clear for everybody? So the rotational plane sweep, so we are going to sort each of these vertices with respect to the angle, and then we are going to proceed vertex to vertex in the sorted order, and we are maintaining the current intersected edges along this line in a binary search tree. So when we come to a vertex, for example, sometimes the edge that lies, so we may come to a vertex like this. For example, look at this one. Look at this vertex. So the incident edge that lies, if we are doing a counterclockwise traversal, this edge is going to, cease to be in the study structure after this event point, right? After we come to this event point, it means that after that point, what happens at this event point is that this edge that was intersecting the rotational half line is not going to intersect this half line anymore. So we need to delete this edge from the study structure, and we need to insert this edge to the study structure. So if a vertex is incident to, if we have simple polygons, it's going to be incident to two edges, and one of them is going to be deleted from the study structure, the other is going to be inserted into study structure. Okay, now so this is the general algorithm is then only this. So what we do is we first sort the obstacle vertices according to the angle they make, and then initially we start our study structure like this. There may be the first vertex that we visit. There may already be other polygons in between, okay? So initially when we are creating the study structure for this vertex, we need to look at all so we need to spend O(n) time to look at all the polygon edges, which ones are going to be in the study structure in our first event point, okay? The first event point, we don't guarantee that we see it, okay? The first event point, when you sort these points, there may be many polygons. Actually, you can have a case in which all the polygons are in between the first event point and this first and the vertex that we are trying to find. Okay, so it may be something like this. So this is the angle it makes with the x-axis. So this is V1, and this is, let me just say V target, and this is V0. The first vertex that, let me just name it as V0, and this one V1 then. So this is V1, this is V2, V3. So we can have many polygons in between, okay? So V2, V3, V4, V5, V6, V7, V8, V9, V10, something like, if you rotate this along this line, we are going to, it may not be correctly sorted, but you get the idea. The first vertex that we are going to, the smallest angle we make here with this vertex, in our first study structure, we need to put all these edges appropriately in the study structure. So we need to spend, for V0 and V1, by spending O(n) time, we check against all the polygon edges, and put into our study structure all the edges that are intersected by this half line. And this binary search tree is going to be such that the edges, all the edges are going to be on the leaves, and on the in the intermediate nodes, we are going to have the farthest node on its left subtree. So it's going to direct our search towards it. For example, let's name these edges E1, E2, E3, E4, E5, and E6. Our study structure is going to look something like this. I mean, if it's balanced, you can use AVL trees or red-black trees to guarantee that it's balanced. So we are going to have E4, and sub3 is going to contain, so this is E2, E1, E2, E3. And these are the leaves. Actually, it's going to be something like this. E2, I'm going to have, if this is the leaf, E3, and I'm going to have another node here, E1, and E2. Okay. And this is actually going to be E3. And here I'm going to have E5, E4, okay, so it's going to be something like this. So each intermediate node gives us the rightmost, the furthermost edge on its left subtree. Okay, which means that, for example, when we come here, we compare our edge with E2. If it's further away from than E2, then it must be into the right subtree. If it is equal to or closer than E2, we are going to continue our search in the left subtree. Okay, so all the edges are on the leaves. So again, for example, when we compare a point, it may be a point or it may be another edge along this line. So what we are going to do is we want to search where we are going to put this new obstacle edge. When we encounter a new obstacle edge, when we are going to insert it into this tree, what we do is we compare this edge with the other edge, with E3, for example, with respect to this pivot point V0 and with this current event point V1. We want to find out whether E4 is closer, in this E new, let me name it E new, whether E new is closer than E3 or not. So we see it's further away from E3. We are going to continue searching on this tree, and we are going to see that it's closer from E5, and we are going to continue from here, and it's farther away from E4. It's going to be inserted somewhere here, okay? So it's between E4 and E5, so it's going to be find its correct place and insert it accordingly in that place. So when we are doing this search, again, what we store here are not just numbers. We are not just storing the distances of these edges along this line, because this distance varies. When you rotate this line, the distance where you intersect these edges is going to vary. But what is invariant is that since we don't have edges that cross each other like this, their order on the line is not going to change. If one edge, E1, is closer than another edge, E2, their order cannot change along this rotational sweep unless they cross each other. And since we have simple polygons as obstacles, we guarantee that their order is not going to change. But again, what we are storing in this tree are not the actual distances of these edges to V0. because this distance varies. I mean, when you're rotating along this line, this distance is going to vary, and we cannot, what we store here as in intermediate nodes are edges. So when we are doing a comparison, we need to, on the fly, do some operations on it, whether this edge is to the right or to the left of this point with respect to this V0. Okay, so we need to make edge comparisons. It's not just a simple scalar number comparison that we are doing when we are searching on this tree. So we are making use of the both endpoints of these edges. Okay, so is this clear? Okay, if no questions, let me just finish the main outline of the algorithm, and then we are going to discuss the subroutine after the break. So the main algorithm is then like this. We first, step one, sort obstacle vertices with respect to the angle they make, with respect to angles, okay, which is the n log n complexity comes from here, and let this row be the half line pointing in positive x-axis. And what we do is find all obstacle edges intersected by row and insert them into our study structure. Insert them to our tree tau. Then actually it's just T, okay? Our study structure T, and then the algorithm is like this. We have a set W, which is initialized to the empty set, and then for all the event points, for I is equal to 1 to n, here this is what we do. If visible, we call a function. If visible other vertices, vi, then add wi to this set W. And what we need to do is insert adjacent edges of Wi in rotation direction to our study structure T, and delete adjacent edges of Wi in reverse direction from T. Okay, so, and that's at the end, we return this W, which is going to give us all the visible. So the set W contains all the visible vertices from a given vertex V. Okay, so this, the algorithm I wrote here is to find all the visible vertices from a specific vertex V. So it takes input as a vertex V. Okay, so there's a pivot vertex V. Then let's first do the sort, and this step is On. And then we initialize a set, and we have what we have here. And this visible function we are going to see in order to find out whether this Wi is visible. we are going to make use of the study structure T, which guarantees log n operations because it's balanced binary search. So this visibility is going to take log n time, and inserting and deleting edges from this tree is also going to be log n time, and this loop is n. So n log n also comes from here. So the overall complexity of the algorithm is going to be n log n. So in n log n time, we'll be able to determine all the set of vertices visible from V. Now, visible from an input point, so input vertex V. Now, the only thing remaining to complete this, our discussion about visibility graphs, is this function, visible WI. So how do we determine, how are we going to determine whether WI is visible from V or not by making use of this tree? The one case, as I said, obvious is that we can determine whether it is not visible if there's an edge closer. By just looking at the leftmost edge, we are going to, in this study structure, we are looking at this E1. If our WI vertex is farther away, if it falls somewhere, if in this search, if it falls somewhere here, it means that there's an edge that is closer to it, closer to the vertex. It means that it's not visible. Okay? In that case, we are going to conclude it's not visible. But if there's no such edge, is it always going to be visible? We are going to decide this after the break. Okay?